Okay, so let's look at a couple of examples of how to compute a Taylor series. I have the formula written here in the summation, using the summation notation, which is, can be pretty brief, as you can see. It's broken into the part that goes from orders 0 through n-1, and then I've written the remainder here just to remind you. And this is the same function, just written out without the summation notation. So our first example, let's write out the Taylor series of cosine x evaluated at x, again, equals a, and in this case, we'll set a equal to 0. So the first term in the Taylor series is just the function itself evaluated at point a, so that's cosine evaluated at x equals a, and that's equal to 0. The next term is the first derivative of cosine, which is minus sine, and that derivative again is evaluated at x equals a, which is equal to 0, and that's multiplied by x minus a. And then the next term is the second derivative. So this is the first derivative. The second derivative is the derivative of sine. So the derivative of sine is cosine, and we have the negative there, and so we have a cosine of 0, again, times x minus 0, and this time this is raised to the second power, and it's divided by 2 factorial. And then if we go out to the third term, we have a derivative of cosine is minus sine, so we have 2 minuses, so I'll keep the plus there, so that's sine of 0, x minus a to the, x minus 0 to the third power over 3 factorial. So we can evaluate these terms. The cosine of 0 is just 1. The sine of 0 is 0, so this gives a 0 in the sum. And then we have a minus 1 times x squared over 2 factorial, which is just 2. And then we have another 0. And then if we were to continue to write out the series, we would get an x to the 4th over the 4 factorial minus x to the 6th over 6 factorial. And this is the series form of cosine function. And I can write that as using the summation notation of the sum from n equals 0 to infinity of minus 1 to the n power times x to the 2n all over 2n factorial. So this would be what you would write for the Taylor series of cosine x evaluated at x equals 0. So now let's look at another example. So this was our first example. Our second one is a Taylor series expansion of the function 1 plus x to the n power, where n is any integer. And we're going to evaluate that at x equals a, and again, we'll set a equal to 0. So again, the first term in the Taylor series is the function itself. So that's 1 plus 0, the function itself evaluated at a, and this is raised to the n power. And then we have the second term, which is the first derivative of the function. So that's n times 1 plus x, but x is evaluated at 0. And so we have an n minus 1, and that's multiplied by x minus a, which is 0. That's this first derivative term. And if we went to the second derivative, we have to take the derivative of this function with x as part of the function. So that's n times n minus 1 times 1 plus x evaluated at 0. and this is x minus a, which is again 0 squared over 2 factorial. And this is the second derivative. For the third derivative, we already have the n and the n minus 1. And this, oh, I forgot to write this out. So, this is n minus 2, right? And so we have to multiply this n and n minus 1 times n minus 2 to get the third derivative. And so on. So if we were to simplify this, this becomes 1. And then we have an n times x minus 0, which is just x, plus an n times n minus 1 times x squared over 2 factorial, plus n times n minus 1 times n minus 2 times x cubed over 3 factorial, plus higher order terms. And this happens to be the binomial series. And this is widely used in physics if we have a function that is raised to an arbitrary power. So this is used, or it's useful, when x is a lot less than 1, because if x is a lot less than 1, you can see that as we take higher and higher powers of x, these terms get smaller and smaller and smaller. So if x is really small, then 1 plus x to the n power, if we take the first linear term as an approximation, so this is an okay approximation. Again, if x is less than 1, and this may be sufficient to a problem that you're solving. A line function is more simpler than a function raised to the n power. So this makes this function quite a bit more simple. If you need a higher order accuracy, you could go to the next derivative, and you would get an n times n minus 1. And this becomes a quadratic function. If you need a better approximation. So these are a couple of examples. I hope you were able to follow this, so you can apply this to your homework or even future projects.